Hello, all of you. My name is Alan Kelly, and I would like to welcome you to our webinar today. A new era of design with MultiJet Fusion is here. My name is Alan Kelly, and in addition to being your host today, I'm also the Canadian 3D printing and additive manufacturing specialist here at Hawkridge Systems. Joining to me today is Liz Stortstrom, an applications engineer from HP. So, for those of you new to Hawkridge, we've been providing engineering and manufacturing solutions to North American companies for over 20 years. And as you can see, we have 22 locations as well as digital manufacturing labs right across North America. And in addition to these products and services, we partner with the leading providers of engineering, manufacturing, and 3D printing solutions. So, Tempest 3D is Hawkridge Systems' newest service provider. Also, Tempest is our first in Canada. So this is a partnership we're really excited about. So I'm hosting this event today from the Kootenay region of British Columbia on location at Tempest 3D. I'm here with Robert Blyer, the CEO of Tempest. And here's a quick interview I did with Robert. Hello, Robert. How are you, sir?
I'm great, Alan. Thanks for coming. Great to have you on site again.
Thanks for having me. You know, you've been open for about 6 months now. How's it going so far?
Yeah, it's been a great 6 months. You know, we were able to hit the ground running with some customers right away. Hawkridge has been a great support for us. You know, whether it was delivery of the initial machine, setup of that machine, and follow-up support has been phenomenal. So I just can't thank Hawkridge enough for everything they've done for us.
Thanks for saying that. That's really nice. If you don't mind, share with us your vision of Tempest.
Yeah, you know, I think it comes down to where we see the additive manufacturing space going. And really, I feel like there's a huge opportunity in additive manufacturing in Canada. At Tempest, we want to be Canada's #1 additive manufacturing service bureau. And we feel like there's a space where we can help customers go from prototyping to production in an economical way and in a way that they can't get anywhere else.
Yeah, so how many pieces of technology do you have, or what materials can you print in?
Sure, great question. So we've partnered up with the Soccer College Technology Access Center here in Trail, BC, and we're able to offer a great variety of technologies and materials, whether it's metal printing with stainless steel, aluminum, or titanium, or carbon fiber printing with some of the composite machines that we've got available to us. You know, Kevlar and fiberglass, they're all great things that we can do. And of course, you know, we've got the beautiful HP 5200 machine behind us, where we're able to manufacture with a really high quality PA12 nylon.
Great. We're doing a design for additive manufacturing webinar today. If anybody who's watching our webinar, you know, if they've designed something and they want to know whether or not it's something that you could print, what it would cost, what do you recommend they do?
Yeah, you know, the best way to reach out to us is to go to our website, tempest3d.com. We've got a phenomenal instant quoting tool on there where if you just want to get one part, you can upload your file. You'll get a price right away. And if you want 500 parts, you can use it there too. We also really like those complex projects and really like to collaborate with our customers. So if you've got something that you've been thinking about or a project that's a bit harder, you know, hit that, get a manual quote, or give us a call. You know, our reps are great. They're very responsive. You'll hear back from someone right away.
Thanks so much, Robert. I am very excited for Tempest, and I'm excited for the future of additive manufacturing. So I really appreciate it, man.
All right.
A big thanks to our partners at Tempest for hosting me and for allowing me to shoot this video with them. Designing for additive manufacturing is a common discussion in our industry. After all, better designs are one of the biggest advantages of 3D printing. So I am very fortunate to welcome one of HP's best applications engineers, Liz Stortstrom, to discuss this very topic with us today. Liz, the floor is yours.
Hi everyone, welcome to a new era of design with MultiJet Fusion. My name is Liz Stortstrom and I'm an application engineer with HP's 3D printing. Now, today we're going to start with a quick introduction to the MultiJet Fusion technology and discuss how that falls under the overarching umbrella of additive manufacturing. We'll also talk about when it makes sense to bring additive into your design cycle. And last, probably we'll spend the most time here, we will explore some different case studies and look at design strategies for MultiJet Fusion. So chances are that if you're in the world of part design or manufacturing, you've asked yourself a number of these questions before. You know, how can we reduce cost in this product? Or I'm working through some design iterations. How can I get these parts to me faster so I can evaluate them? Or, you know, we've been doing this the same way for a number of years. What are some new innovative ways that I can bring more value to my customers? So to answer these sorts of questions, we really need a thorough understanding of our manufacturing options. And we can group a lot of these techniques into three broad categories. So subtractive manufacturing, this refers to things like CNC machining, where you're removing material. Formative manufacturing, this refers to things like injection molding or extrusion. And then the reason we're all here today, additive manufacturing. Now, I think it's good to point out early on that additive manufacturing is not going to replace these other technologies outright. Instead, we look for ways to complement these traditional processes in order to optimize our overall approach to production. Now, when we talk about additive manufacturing, this really refers to a broad range of technologies, and they all have their own strengths and weaknesses, which means, you know, they each have their own place depending on what your objectives are. The common thread here is taking a 3D model and generating a physical object by building up the material, typically layer by layer. So you're likely familiar with a number of these. We have FDM under material extrusion, SLA, which was actually the first 3D printing technology, and then also SLS, selective laser sintering under powder bed technologies. Similarly, MJF also falls under the category of powder bed. And this means that we spread thin layers of powdered material, so it eliminates the need for any support materials like you might be used to with FDM, for example. So going a bit deeper into the fusing process, after we spread the material, we have a print carriage come across and print fusing and detailing agents using HP inkjet print heads. And so these are the same inkjet print heads we use in 2D printers. It's the same exact process. We're just leveraging it for this 3D technology. At that point, everywhere that we've placed the fusing agent, that's where we're going to absorb the most energy and the part is going to fuse together. Of course, this whole time we're monitoring the temperatures with a thermal camera just to make sure that we are fusing correctly, keeping everything at the right temperature. Once that layer is complete, we lower the platform, spread a new layer of powder, and that process repeats until the entire build is done. So with this approach, we can actually achieve nearly isotropic strength throughout the entire build chamber because the material is not being fused just within the layer, but also across the layers, which traditionally has been a difficult problem for 3D printing technologies. So I'd like to just clarify a couple misconceptions. This is different from binder jetting because we are actually using an ink or an agent, not a binder. And all that agent is doing, it's controlling how much energy is being absorbed where in that print bed. And similarly, we're not actually jetting a material, we're jetting the agents, and the material is the spread powder itself. And in both cases, MultiJet Fusion can achieve higher mechanical properties, more durable parts, because we're actually fusing that polymer together. So I know we talked about how SLS is similar to MJF in the fact that they're both powder bed fusion techniques, but there's also a number of differences. SLS delivers energy, of course, with a laser, so it's this single point. So it has to traverse the entire fuse area of a part in order to melt that material together to fuse it. But with MJF, we're actually working with infrared lamps that are the entire width of the print bed. And so we're able to just move this carriage back and forth along one axis, and we can actually move much quicker. So we can print a layer in about 8 seconds, regardless of the part complexity or the number of parts that you're printing on that layer. The other piece here is that since every voxel or volumetric pixel is exposed to energy for a longer period of time, the material itself doesn't have to be as reactive as is typically the case in SLS. So if you have lower reactivity, that means you have lower degradation of the material over time. And that's what allows us to use up to 80% recycled material job after job, which ultimately saves you costs, but is also just a more sustainable process. Okay, so with all that in mind, we start to get this idea of when and where the technology makes the most sense. And not just areas where we can use it, but applications where there's really a value add in using MultiJet Fusion. So if we look in transportation and industrial, there's a lot of value in the isotropic strength of the parts, also the ability to take a part that was previously machined and turn it into a 3D printed part. You're going to save a lot of weight. And of course, a number of these applications require fluid tightness, which MJF can achieve. On the medical and consumer side, you can really take advantage of this idea of mass customization. So instead of mass production where you're printing or where you're creating the same part over and over and over again, here we can actually design a robust final product that is unique for each individual user. All right, so now that we have a good baseline understanding of the technology, when do you decide to use MJF? A great place to begin is prototyping. And I know a lot of us are familiar with that. OAKLEY, this is one of the world's leading product design and sport performance brands. They have a lot of focus on driving innovation when it comes to the design of their products. So they're always searching for the latest and greatest. Now, OAKLEY recognized this industry shift towards 3D printing, and they really wanted to use it to streamline their prototyping and production processes. So they actually looked to HP's JF580 system because this allowed them to experiment with designs and achieve a faster time to part than with other additive technologies they've tried. And at this point, they've used it for a number of applications, including helmet prototypes. So they're stronger and lighter than with other technologies they've tried. They've also used the color-enabled system to differentiate features in their prototypes, like in this picture here. And they've also used it for things like even trophies for their internal employee events, which is really fun to see. But the truth is that since the MJF technology is quite capable and quite robust and allows for this higher throughput, we can actually move beyond just prototyping. So it means that we can use MJF for full production when we're talking about low to mid volume applications, or sometimes bridge production when we're talking about higher volume products. This is where, say you're not sure what your volumes are going to be, there's some question in your production approach. It's great to be able to leverage 3D printing in the bridge production phase before making a decision to tool. And then of course, after your product is already in the market, there are a number of opportunities to save on cost and physical space by moving to a digital inventory. and printing spare parts. And finally, at any point in your product life cycle, you can also use additive in the form of manufacturing aids like jigs and fixtures. So let's take a look at a few more examples. So Xtal is a company that specializes in automation and engineering services and plastics assembly technology like welding. They've been running one of our latest materials, polypropylene, and they've been quite successful with this because they've been able to leverage the manufacturing industry's familiarity with polypropylene. So they were able to introduce customers into this world of additive and ultimately help them decrease their time to market. In this particular example, we're looking at a fluid reservoir prototype. It used to be injection molded because they required functional testing. So that meant that the prototypes actually needed to behave like the final part. But by moving to MJF, they reduced their lead time from 7 weeks to 6 days, and they still had a hermetically sealed part, and the burst strength was very close to the injection molded part. So this time savings is not just useful in prototyping like we've been talking about. So Xtal is also starting to use this strategy for bridge production applications as well. CGX, they design and manufacture these wireless monitoring systems. Most notably, it's EEG headsets. And this latest product here, this is the Quick 20R, this has 20 different channels to monitor your brain waves. So in this scenario, CGX builds low volume, highly specialized systems, so they can't really justify the cost and the lead times associated with tooling. So they started experimenting with MJF for functional prototyping, and initially they were just ordering through a service provider. Now I want to take a moment to say that this is a great way to dip your toes into the world of additive because you can leverage the service provider's expertise to make design iterations, including making any adjustments for cost and time savings with this process in mind. But eventually, CGX switched final parts to MJF and even started making some molds out of MJF because it was consistent and it lasted longer than their previous methods. And at this point, they have about 95% of these headset parts being made with MultiJet Fusion. All right, so this is one of HP's own examples. The America's Product Completion Center, or APCC, they run 19 different packaging lines for HP inkjet supplies. Here you can see a picture of some sprocket media. And these lines undergo frequent changes since they need to adapt for different packaging and for different regions. So the APCC actually started with FDM printing, but pretty quickly realized they needed something a bit more robust, a bit more capable of producing parts at volume. So the APCC adopted the MJF technology to design, to test, and to produce parts more quickly. So for them, the biggest benefit was eliminating the need for outsourcing while also reducing cost. They now use the technology for a wide range of applications, including conveyor belt parts, end-of-arm tooling, spare parts, break fix parts, and even jigs and fixtures. Within about 3 years, they have already saved over $400,000 with this technology, and it's become this integral part of their overall manufacturing process. All right, so now that you have a good idea of when MJF makes sense to use, we can start to dig a little deeper into how to design for MJF. If you consider a product design cycle, you can introduce additive at any point. Earlier on, there may be more opportunities since the exact geometry of the parts is going to be less defined. But even when your part design is pretty much set, there's still always a way to take advantage of additive. So let's start there. Assuming your part design is fixed or nearly finalized, there are still ways to use additive to save on cost, to save on weight, and of course, time to part. So in this situation, you probably have to keep at least the external geometry of your part the same, since it might be mating to another part or need to fall within some specific space constraints. But you still may have the option to lightweight the parts. To do this, we're looking at part design from kind of the opposite lens of subtractive technologies, because in machining, you would likely try to minimize operations to save cost. But with additive, the priority is often to minimize the amount of material used in order to reduce cost or even weight of the part. And there are a couple simple ways to do this. So we have hollowing the parts. You could add a honeycomb or even a full lattice structure as shown on the right. And the choice really depends on what level of structural integrity is needed for your part's function. But in any of these cases, there are plenty of software options that have these functions available. And if you aren't sure where to start, feel free to reach out to myself or your contacts at Hawkridge, and we can definitely help you out and put you on the right track. I'll also add that you can either leave an opening for powder to escape if you've hollowed a part or put a lattice there, or just keep the geometry closed and leave the unfused powder inside the part. Since ultimately the unfused material is less dense than the fused part, you will still be saving on material and agent usage, even if it's enclosed. Beyond just lightweighting, you won't have a lot of options to take full advantage of unless you start earlier on in that development cycle. So next, we'll take a look at these three strategies: designing for process optimization, designing for assembly, and designing for performance. And this is what you can do when you're really starting with additive manufacturing from the start of your design process. So working backwards, to talk about designing for process optimization, we have to consider the specific process. So like we talked about at the beginning, there are a lot of different additive manufacturing or 3D printing technologies. So in the case of MultiJet Fusion, it's a thermal process, and that thermal experience that every voxel has as it's being fused and then as it's being cooled, that's going to affect the final part. This is an image from one of our printer's thermal cameras, and of course we use this camera to control the heat delivered into the bed from layer to layer. So while we can technically model any combination of parts and geometries to print, really in order to achieve the most consistent results and the highest repeatability, we still want to pay attention to how we're designing and positioning parts in our build. So aiming for a fairly even distribution of fuse area across the whole build volume is going to lead to the most consistent part quality results. So with this idea of consistent fuse area in mind, we start to trend towards more skeletal designs. So looking at this part as an example, it was originally designed for injection molding. And because of that, it required a continuous section for the material to flow. We, of course, no longer have that limitation with MJF. And in fact, printing less material is going to save on your part cost and help with this idea of maintaining consistent thermal experiences across the entirety of the part. Now, this is a very simple example, but this approach is the same for even very large, complex 3D geometries. And what's nice about MJF, again, is that that complexity comes for free. If you're printing a complex 3D structure with FDM, material jetting, you would need a lot of support structures, and that's excess material that you're paying for. But with the powder bed approach, we don't need that support material, so the process remains quite efficient, even for very complicated parts. So another place HP found a great opportunity for switching to MJF was in our large format latex printing business. In this case, the printer was already in production, but they were looking for ways to reduce cost and weight for several of their machined components. Let's take a closer look at one of these. And what you can see here is the design progression for one of these components. So what started as a machined block all the way at the left ended up as this topology optimized structure with a 93% weight reduction and also a 50% cost reduction. And the cool thing here is this is a design that's only achievable through additive manufacturing, and it allows for the most efficient approach to design in terms of performance and also your material usage. But the other thing this shows us is that you don't necessarily need to jump to the most optimized solution. By even taking that first step, there was already a substantial weight reduction from the 355 grams to the 80 grams, right? So we really don't necessarily need to go down this entire progression. Ultimately, it's going to depend on your part's function and also your time and resources. So besides from designing for the process, we can also design for assembly. Without the same limitations as traditional manufacturing techniques, we can now consolidate parts that we used to have to assemble together. This example is a drill extraction shoe, and it's this device that we use in manufacturing HP's print head nozzles. It basically removes the silicon sludge and water from the machining process. So it makes the whole laser drilling process more efficient. So what we did here was consolidated the design from 7 parts plus a number of fasteners into one MultiJet Fusion part, which enabled 95% cost reduction and also a 90% weight reduction compared to the original. And the original primarily used, again, machined aluminum parts and some standard off-the-shelf parts. So this part is a great example of designing for an assembly, and it's still in use today on our manufacturing lines. Here we have a duct that's actually in our 500 series printer. And this is a great example of what can be done if you're designing for performance from the start. So the original design was made for injection molding, but there were actually a number of limitations. The blades on the bottom were too thin for the material to flow. The sidewalls needed draft. There were also lots of assembly steps with these 6 different parts and fasteners. So in this case, the design for additive was actually a simpler process compared to designing around all of the injection molding constraints, right? And we see a lot of MJF parts used for ducting because unlike some other technologies, MJF is actually airtight. But to take this design to the next level, we actually worked with Siemens and they ran a CFD analysis to demonstrate how you could optimize a duct's shape to even further improve the flow rate. Now, I like this example because there's no way, you or I could have dreamt up this shape, but by using the right tools for the job and the right technology, you can come up with some really unique solutions. All right, so beyond these 3 main strategies, you'll also want to consider minimizing your costs as much as possible by design for packing. So to get the most out of your printer's build volume, we want to pack parts efficiently within that build volume. And for MJF, increasing that build density or the number of parts in your build will not only lead to higher throughput, but also overall lower cost per part. So an easy example of this can be seen on the left, where you're simply stacking these cup-like parts. And if you maintain good clearance, which is usually between 5 and 10 millimeters, you'll have fairly consistent fuse areas per layer, and you can fit a high number of parts into the build. You may also find you have parts like on the right where they can fit nicely together side by side or fit together like puzzle pieces. Now, in reality, parts don't necessarily always fit like this together. There's a lot of parts that have straight walls and right angles because that's just how we're used to designing. But in a lot of cases, you can look for ways to either tilt these surfaces or, adjust the design to fit together a little better, and it can lead to a great deal of cost savings. So one example of this is from Avid Product Development. Now, you may or may not have seen that there have been a lot of 3D printing applications popping up in response to the COVID-19 pandemic. I know HP and Hawkridge have been working to support a number of these efforts, anything from stopgap surgical masks to nasal swabs for testing. In this example, we're looking at a face shield design from Avid, and the way it works is that the frame is what's printed using MJF, and then they use a thin plastic sheet to form the actual shield. Now, originally we were printing face shield frames curved since that's its final form, right? But this quickly proved to be inefficient, especially during this time when everyone is trying to crank these things out as quickly as possible. So we soon moved to an unfolded design that packs much more efficiently. Then all that happens is after printing, you can simply bend the part and snap it together using these built-in fastening pins. So now they can actually print nearly 300 of these in a single build, which means they can make almost 300 face shields a day, which is great to see. All right, the last topic I want to cover is designing for functional color parts. So HP's JF580 has the ability to print full color parts, but what sets this apart from some other technologies is the functionality and the strength of the color parts. This is pretty unique in the additive manufacturing space because historically, technologies that are fully color enabled also have pretty weak mechanical properties, which is not the case with MultiJet Fusion. So it's opened up a wide variety of new possibilities. And we can summarize the process for adding color into a couple different categories. So on the simplest end on the left is just adding color to an entire part. This could be useful if you're just trying to color code parts, say if you want to track design revs as you're going through design iterations. In the middle example, it's also fairly simple to add color to faces. And a lot of designers use this trick to simplify the color application process. If you can engrave a text or label slightly into a part, then you'll have a unique surface that will be easy to change the color on. But to take full advantage of color, we refer to texture mapping, which can be seen at the right. This is also a concept used in gaming where you would take a 3D object and wrap an image around the geometry in a specific way so that the final 3D part with color appears the way you intended. And that way you can work with a 2D color image and a 3D mesh object. So as you can see at the right, you can achieve some really impressive designs using this technique. But a lot can also just be accomplished with this simple middle approach. And a great example of this is with manufacturing aids and jigs and fixtures. So these parts need to have a high level of durability, mechanical strength to withstand their everyday use and also interact with other parts. And this same part could have been printed in one color, but look at these various things that we can do when we're adding these different color surfaces, right? We have red and green to call out different critical surfaces. There's a QR code printed directly onto the part, which could reference anything. It could reference part numbers or even instructions for using the tool. And you can also just print text, instructions, safety labels directly onto the part, and it becomes more legible. So these sorts of changes may seem novel at first, but they actually lead to improved efficiency and reduction of mistakes on the manufacturing line, which at the end of the day can save you both time and money. Seb Automatisme is a systems integrator in France, and they work with industrial customers to test out 3D printing ideas. They utilized color for this really unique part. It's a robotic gripper that picks up a part from a final step of production and places it onto a storage shelf. So the innovation in this design actually lies in the fact that these 3 different colors are used to designate different areas of the gripper where corresponding pneumatic cables need to be connected. So this just helps with cutting down assembly time. Beyond that, though, by moving to MJF, they also eliminated a lot of excess cables and tubing, since all of that was integrated directly into this part. And it also saved a tremendous amount of weight in the tool. So both of these benefits allowed for smoother and faster operation of the robots, which ultimately increased their production speed. This is a great example of a part that simply could not have been made with any other manufacturing technique. All right, since we've been talking about color, I want to wrap up with an example from our color-enabled JF580, because it really encompasses many of the strategies that we've introduced today. The development of this printer was actually quite an undertaking. There was a lot of new technology that went into the system. And of course, along the way, we ran into a couple technical hurdles. So ultimately, we had to add 2 new subsystems that were not in the original plan. But of course, since we already committed to a delivery schedule by that time, traditional manufacturing techniques would not have supported us to meet those deadlines. So to make this possible, the engineering team came up with a new strategy. They used standard or simple, easy to fabricate components like sheet metal for all of the low complexity features. And then they pushed all of this system complexity into MultiJet Fusion parts. That allowed them to design, to test, and to iterate very quickly, since all that iteration was done on the MJF parts. And of course, those parts could be printed in a single day. The other advantage here was that the prototype technology was the same as the final manufacturing technology. So you're already testing the final product behavior when you're running prototype tests. This strategy saved a lot of time for them because there was no design of plastic tooling, and the only hard tooling required was for sheet metal parts, which again was relatively fast since those parts were not very complex. So all in all, the reduction of the development time was estimated between 13 and 26 weeks, which allowed us to fit these subsystems into our final product. Today, there are over 200 parts or 141 unique MJF designs in this printer. And you can see many of them pictured on the right. So besides from this design flexibility and speed to part, it also resulted in a huge cost advantage in a couple different areas. So the first area was that we designed some final parts for MJF. The second, we used MJF for bridge production instead of immediately going to tool. And then third, we created MJF parts that eventually were obsoleted, right? Some things change. You don't necessarily need all the parts in the end. So between these 3 categories, the team was able to avoid or defer nearly $5 million in costs due to tooling, right? Which is huge. And when we start considering the flexibility and the control over when to invest in tooling by designing multiple parts for MJF, it really starts to add up. All right. So to summarize everything we discussed today, we can now strategically complement traditional manufacturing techniques with additive manufacturing to create really innovative products. We're no longer so tied to the cost and time associated with hard tooling, and we can even avoid additional post-processing steps like painting and labeling just by printing directly in color. So if I can leave you today with just one message, it would be that the world of manufacturing is evolving, and to take full advantage of it, our approach to design needs to evolve with it. Thank you.
Thank you so much, Liz. That was fantastic. I have two questions for you, Liz. One is about organic structures. Can you speak to that at all, about the, how to design organic structures?
Sure. And I mean, there are a lot of different approaches. One of the approaches that we talked about just now was topology optimization. And so that could be one thing people have in mind when they're thinking a more organic shape, which is simply using a program to run an analysis to look for, okay, maybe I don't need this whole block section. Where exactly are the forces being applied to this part, and where exactly do I need structure? And so in the end, the resultant part may be something totally different from what you could imagine, but is ultimately the most efficient version of that part. Otherwise, another interesting area to look into would be lattice structures, and there are a number of different cell designs and cell structures, some that are quite organic or kind of random in nature, and they each have their own kind of benefits. It depends on your application and what kind of response you're trying to get out of your part, whether you're working with a rigid part or like a more flexible elastomer. But yeah, really anything you can imagine, of course, ultimately you can print. So just go for it.
Cool. Can MJF make clear, translucent, and/or transparent parts?
So yeah, this time we don't have an option to create translucent parts. Technically, if you're printing a thin enough section, it is translucent. And so we have seen applications where, say there's like a button and it's a solid, but then we've actually thinned down the wall in a certain section and there's a light behind it. So you've got a backlit button situation. You could see the translucency in that case. But as far as just like a straight transparent material, we don't have that.
Okay. Well, Liz, those are the only questions that we have for you today. I can't thank you enough for taking the time to do this with us today. To all those that are listening, please feel free to reach out to Hawkridge. Hawkridge Systems will put you in touch with your local rep, and our 3D printing reps can talk 3D printing with anybody all day long. It's what we do. We love chatting about it. So please, whether your question is big or small, if you're wondering if this is good for you or good for your business or good for your startup, please feel free to reach out to us. And so with that said, thank you, Robert Blyer of Tempest. Thank you, Liz Stortstrom of HP. And goodbye, everybody.